with is that the solutions are when the cosine of x equals negative 0.78 and the cosine of x equals 0.28. So let me just work through that and finish it off. So there's 4 solutions between 0 and 2 pi, but the question is how many of these solutions are between 0 and are between the values of x that we had as the endpoints. It may not be 4. So let's see. But this gives us some practice for me to show you, how to use the reference angle thing. So here's your cosine of the angle. So what you do is you find the reference angle, which is going to be the inverse cosine of the absolute value of negative 0.78. So I need to get my calculator. So by doing this, when you use the reference angle, well, when you take the absolute value, you always put it in the first quadrant, which the reference angle is always a first quadrant solution. So let me make sure I'm in the right mode here. We keep switching from physics to calculus and okay, let's try that mode. Quit. There we go. Okay. So we take the inverse cosine of 0.78, which is the absolute value of negative 0.78, and you get the reference angle, which in this case is radians. So you get 0.676 radians. And then we multiply by pi and divide by pi. So if you take this and divide by pi, you get 0.215 pi. So the second part is pi radians. So that one is in the, well, these are all in the first quadrant. Let's go ahead and, what was the other one? 0.28. Let's do the other one over here. Cosine of x equals 0.28. So the reference angle associated with this part is the inverse cosine of the absolute value of 0.28. So what's that? The inverse cosine of 0.28 is 1.287 radians. And then we divide that number by pi to get 0.4097 pi radians. And the question is, which quadrants are these in? So I'm going to ask you about that. So think about, so when you have a negative cosine, think about the unit circle. Which quadrants is the cosine negative? And remember, the cosine is the x-coordinate. So which, basically you're asking, when you do this, you're asking what quadrants have a negative x value. So Hannah, what quadrants have a negative x value? Yes, it's going to be, so this one's going to be a second and third quadrant solution, and as a consequence, we know what the answer is here. It's going to be the first and fourth quadrants. So this is second and third quadrant, since the cosine is negative. If you think about that, if you draw a unit circle, just sketch it in there. Remember, the sine is the y-coordinate and the cosine is the x-coordinate. So the x-coordinate is negative in the second and third quadrants, and the x-coordinate is positive in the first and fourth quadrants. So this one's going to be Q1 and Q4. So here our two solutions are going to be, my second quadrant solution is going to be pi minus the reference angle. So you get pi minus 0.215 pi, which is going to be 1. So it's 1 minus 0.215. So you get 0.785 pi. So that's my second quadrant solution. My third quadrant solution, theta, is going to be pi plus the reference angle. So you get pi plus 0.215 pi, which is 1.215 pi. So that's my second solution. And then over here, the first quadrant solution is just the reference angle. So theta is equal to the reference angle. So that's, what is my reference angle? 0.4097 pi. And my fourth quadrant solution is 2 pi minus the reference angle. So I take 2 minus 0.4097. So what I'm doing here is I'm taking 2 minus 0.497 pi, because these are all in terms of pi. So all I have to do is, this is 2 pi, this is 0.497 pi, so to get the answer I just subtract 0.4097 from 2, which gives me 1.5903 pi. So those are my 4 solutions. And what those are, remember, are where the slope of the tangent line to the curve is equal to the average slope between the endpoints. So what we had done is if we go back to the beginning here, is we had evaluated the function at the beginning and the end of the interval, got the y values. So we took the difference in the y values divided by the x values, which are this, and we come up with an average slope of negative 1.126. And then we said, what values of x does that make the local tangent line, or the local derivative, equal to the average derivative, basically. And so these are solutions I came up with. So let's plot that function again. What was the function? It was 2 cosine x plus, oh no, the function is 2 sine x plus sine of 2x. Okay, so let me go ahead and plot that. You take attendance here in a second. Where's my graphing program? Here it is. So the function we're looking at is 2 sine x plus sine 2x. And we were looking between pi over 4 and 5 pi divided by 3. And we'll graph that. Okay, so there it was. And so what we've come up with here with the solution is that and let's put this in terms of pi. So we're going to put the x units in terms of pi. So let's see which of our solutions are in this domain. 0.785 pi, 0.785 pi, that's right here. So what it's saying, what we just did through all this math, is we're saying that the tangent line to the curve here is the same as the line, the slope of the line that connects the endpoints. And that looks like about right. Okay. Let's see what the other one was. Let's see what the others were. So it's between 0.3 pi and 1.7 pi. So let's see what we got. So this was between those two. That one's 1.215 pi. So let's do that. 1.215 pi. So right here, the slope of the tangent line is equal to the slope of the line connecting the beginning and end. That looks reasonable. Let's see what about the other two solutions. Let's see if they're in there. 0.4097 pi. So if we go to 0.4079 pi, that's about here, which again looks like about the right slope. And then the last one is 1.5903 pi. So that's about right here, which again they're all negative slopes, and they look about a slope of 1 approximately, so, or about the same slope as from here to here. So that's the whole idea of the mean value theorem. It says that if you have 2 points in space on a graph and you connect those 2 points with a line, the slope of that line is equal to, there's at least one value of x between the beginning and the end where that local slope is the same as the average slope. In this case, it turned out there were four 4 values of x where the local slope was equal to the average slope. Okay, don't worry, I'm not going to give you anything that difficult on the test, but hopefully some of you said, oh, that's pretty interesting. Okay, we're going to move on to section 3 now because we finished everything. So in section 3, we're going to talk about tests to determine whether a critical number is a local minimum or maximum or neither one of them. At the next section, we're going to talk about what's called we're going to use the first derivative test here. In section 4, we're going to use what's called the second derivative test to determine whether you have a local minimum or maximum or neither. And section 5, we actually talk about something that you've already had, which is horizontal asymptotes. You might, that seems out of place in this particular chapter. And the reason we talk about horizontal asymptotes in section 5 is because in section 6, we talk about sketching graphs. And what that does is it uses all the stuff we've learned in pre-calculus and calculus to give the most accurate way to sketch a graph without plotting a lot of points. Okay, so that's kind of where we're going with this thing. But let me just demonstrate one thing here. So let me add a page. So let's say we have the function f of x equals x cubed. So if I asked you find the critical numbers, so the critical numbers is where the function is, the derivative is equal to 0 or where the derivative is undefined. So first thing we do when we're finding critical numbers is we take the derivative. So you get 3x squared. Okay, so we'll say at what values of x does f prime of x equals 0 or f prime of x is undefined. Well, because it's a polynomial, it's always defined, so we don't have to worry about that. The other one's easy, right? X equals 0. When x equals 0, the derivative equals 0. So you might be tempted to say, based on our previous experience, you may say, oh, there's probably a local minimum or maximum at that point, because we've had the experience where the first derivative is 0, we have a local minimum or maximum. But if I plot this function, y equals x cubed, you should remember what this looks like. Looks like this. Okay, so that's y equals x cubed. So here's x equals 0. And obviously, we don't have a local minimum or maximum at this point. We do have, I didn't draw it exactly right, but it comes in here and it has a 0 slope here, and then it goes, so it's always positive slope, and it goes to 0 here, and then it goes positive again. So there are examples where having the first derivative equal to 0 does not give you a local minimum or maximum. So we have to have some way of determining that, and that's what the first derivative test allows us to do, is to figure out whether something has a local minimum or maximum. So before we do that, we're going to talk about what it means to be an increasing function or decreasing function. It's what you would expect. So this is not rocket science. So there's a couple of ways to look at this. You can say as a function increases, the derivative is positive. As a function decreases, the derivative is negative. So here we're just making observations about the derivative. So let's see what that's saying. So here's a graph. Here's some coordinates, and actually we could make it a little bigger, because I'm only going to show one graph. So let's just do a parabola. So as a function decreases, so this is where it's decreasing. Decreasing just means that as x, as you go to larger and larger values of x, the value of the function becomes less. So it's going downhill basically. At this point, the slope is 0. It's not going up or down. And then when you come over here, the function is increasing. As you know, this always relates to whether you're always going from left to right. So if you're going from left to right, the function is decreasing, then the derivative is negative. If you're going from left to right in the x direction and the function is increasing, then you have a positive derivative. You know, if I drew my tangent line to the curve, you can say I have a positive slope. Here I have a negative slope. Okay. Nothing you didn't already know. Okay. So the next thing is functions change from increasing to decreasing and vice versa at critical points. So that's a relationship between critical points and the graph. Now the opposite is not true. At critical points, the function changes from increasing to decreasing. It could, but it doesn't have to. We gave the example where there is a critical critical point where it doesn't change. But we do know that when you have a local maximum, in this case where you change from increasing function to a decreasing function, that at that point there is a critical number. It is a critical number. Likewise, when you go from decreasing to increasing, the point where it changes from going one direction to another direction is going to be a critical point. So the first derivative test, I'm not going to formally say it yet, but the first derivative test basically says, let's find out where the critical points are, and then we'll look at the function to the left, and we'll look at the function to the right, and if it changes from decreasing to increasing, then it's a local minimum, and if it changes from increasing to decreasing, then it's a local maximum. That is the first derivative test. So let's just work a problem to show you how to do this. So basically the procedure is we find the critical numbers, which we've done before. What you do is you take the derivative. When you find the critical number, you're basically finding where the derivative is 0 undefined. So these really go together. And then what you do is you evaluate the derivative in the intervals defined by the critical numbers. And then you make some kind of observation. So I'm going to just follow the steps here. So step number 1 for doing the first derivative test is you take the derivative. F prime of x equals 3x squared plus 9x minus 12. You can see here when I take the derivative here, I get 2x and the 2's cancel out. Okay. Set f prime of x equal to 0. And that should not have an exponent to it. Okay, I'm going to divide by 3, so I'll get x squared plus 3x minus 4. Okay. And then we can factor it. X minus x plus 4, x minus 1. So you can see that's a correct factorization. And so for this to be 0, each one of these has to be 0. So we set x plus 4 equal to 0. We set x minus 1 equal to 0. And so we get at x equals negative 4 and at x equals 1, we have the derivative equal to 0, just like we did for critical numbers. We also should look at whether the derivative is undefined at any point, but it's not. So the only thing we have to worry about here is zeros. Okay, so that's exactly what we did in section 1. There's nothing new there. What we're going to do now is we're going to create a table and define the intervals. So what it said here is evaluate the derivative in those intervals defined by the critical numbers. So what you do is you take the domain of the function, and I got to remember how many rows I need here. I need, I think I need 4. I'll make 5 just to have an extra one if I'm trying to remember exactly what I need to put in these. Okay, yep. So here's our table. So the best way to do it is to put it into a table. Do these calculations in a table. And the number of columns is dependent upon how many critical numbers you have. So I have 2 critical numbers, so I'm going to have, you always have one more interval than the critical number. You have one more interval than you have critical numbers. You'll see why in a second. And you need a column for the descriptors. That's what the first column is for. So let me just fill this in. I'm going to write an interval here. And one interval is from -infinity to -4. Another interval is from -4 to 1. And another interval is from 1 to infinity. So, the domain of this function is -infinity. X is greater than -infinity and less than +infinity. Unless you're told otherwise. Unless you're told otherwise, the domain that we look at is the domain for the function. So if I had the square root of x, I wouldn't include negative numbers or something like that. For trig functions, we could do -infinity to +infinity, but we typically use 0 to 2 pi. So for one oscillation. Okay, then we have, let's see, we have, what do we do here? Oh, yep, I only need 4 rows, but I wasn't sure. So here is, what do I want to put here? X. And then we evaluate the derivative, f prime of x, and then we make some comment. And we don't need this last row. So if we picked x equals -4 and evaluated the derivative, what we would get is that the derivative is 0. Okay, that's why we don't include -4. But because a function can only change from increasing to decreasing across a critical number, then I know that in this interval, anywhere in this interval, that it's going to be either an increasing function or it's going to be a decreasing function. If it changed from increasing to decreasing at some point, I would have found a critical number. So I use the critical numbers to break it up such that each interval is either going to be defined or demonstrated to be increasing and decreasing. So I have to pick some value of x between -infinity and -4 where I can evaluate the value of the function and see whether it's positive or negative. We don't care what the value is, we just care whether it's positive or negative. If it's positive, then it's an increasing function. If the derivative is negative, then it's a decreasing function. Okay, so I'm going to, you always pick the numbers that are easiest to evaluate. So I'm going to pick -5 here, which is in this interval. It's the, you want to pick whole numbers or integers. I don't pick -4 because I know that's going to give me 0. So that's the next more negative number. Here I'd probably just pick 0 because 0 is between -4 and 1, and 0 is always easy to evaluate. And then here I'll pick 2. So 2 is the next larger integer compared to the number that defines the interval. So once I've picked those numbers by just looking up here and deciding, I mean, I could pick -10 or 1 or -1. Any number in here is going to be fine. So then what you do is you evaluate f prime of x, not f of x, but f prime of x at the values of x chosen in the intervals. So let me add a page here. So first we need to do, what is f prime of x? It's 3x squared plus 9x minus 12. So let's just write down what f prime of x is. 3x squared plus 9x minus 12. So we're going to evaluate f prime at -5. We're going to evaluate f prime at 0. We're going to evaluate f prime at 2. So go ahead and plug those in and see what numbers you get. And the one for 0 is easy. It's -12. I can do that one for you. So Cassie, what'd you get? I see you got an agreement there with.
I got 18 for -5.
18? Okay. And what'd you get for net 2? 18? Yeah. You do see that a lot when there's symmetry involved in these situations. But so what we do is we take the result of those calculations, and all we have to worry about is the sign. So the result of that is positive. It's a positive number. This is a negative number. This is a positive number. So we put a positive here. We don't put the number. We just put a sign. And we put a negative here, and we put a positive there. So from these signs, we can say whether the function is increasing or decreasing. So this is increasing because it's positive. This is decreasing. And this one is increasing. So the first derivative test says, we'll show you what it says in detail in a second. It says that if a function goes from an increasing function to a decreasing function across a critical number, which it has to, then it's going to be a local maximum. And if it goes from decreasing function to an increasing function across a critical number, then it's going to be a local minimum. So you can look at the words, but you can just think about what's going on here. If I have a function, let me move this down a little bit, well, actually, I could use this last column here. Let me just erase that. So if I just draw a line, here's increasing, okay? That's my graph. Here's decreasing. Here's increasing. So based on this, do you think we're going to have a maximum or minimum here? Lexi. Yeah. Right. And what do you think we're going to have here? Minimum. Yeah, just as you would imagine by looking at the lines. So actually, I hadn't done this before, but I may actually do this because that way I'll force you into doing this. So we're going to have an additional row here. And so if you just draw a line that represents what's happening here, so the positive slope means it's increasing, which visually we can draw as a line going this way, and decreasing like that, and you can just look at it and you can say, oh, that's got to be a maximum, right? And this has got to be a minimum. That's a valley, and there's a mountain. So the way you would formalize this is you would say, let me add a page in between here. Since f of x changes from an increasing function to a decreasing function at x equals -4, there is a local maximum at x equals -4. Also, since f of x changes from a decreasing function to an increasing function at x equals 1, there is a local minimum at x equals 1. So when you have the test on this material, the first derivative test problem looks very similar to this. It's going to be a polynomial. You're just going to have to factor it to find the critical numbers. And then you will create a table where the interval from -infinity to +infinity gets broken up. You'll pick values of x that are in those intervals to figure out whether it's increasing or decreasing by evaluating the first derivative. And from the information about whether it's going from increasing to decreasing or decreasing to increasing, you can use this reasoning to determine whether it's a local minimum or local maximum. So it's not really that's pretty straightforward. I think most people don't have problems with it. The problem we have here, let me explain to give you pitfalls. Okay. And I'm going to do this because I'm trying to, so you don't have the pitfalls. Okay, notice the evaluating the derivative. Notice that I use that. Now, if I use this, if I said f prime of x was x squared plus 3x minus 4, I'd get the same, not the same derivative values, but I'd get the same I would get the same signs. And so it really wouldn't matter whether I use this to calculate f prime of x at these values. And the reason you might want to use this is because this one you might have to multiply everything by 3, so it's tempting to use that. The problem you run into is if this were a negative number and you divide it by -3 to get to this, you always have to make sure that the equation that you use to evaluate the derivative has the proper sign. You can use the simplified version, but you can only use it if the sign in front of the x squared term is appropriate. If it's not, you're going to get the opposite answer. And that's where people make mistakes. Okay, so that's what we just did. Yeah, so here's the formal definition of the first derivative test. We just used it, but when a function goes from increasing to decreasing as the value of x increases, you have a relative maximum. When a function goes from decreasing to increasing as the value of x increases, you have a relative minimum. So it's called the first derivative test. It's because we're using the value of the first derivative to determine whether the function's increasing or decreasing, and if there's a change in that across a critical number. The second derivative test, we'll use the second derivative to answer that question, but that's not till the next section. Before you write that down, okay? So why don't you try that problem? So let me put this on one page so you can see it. So this is a cubic. It's missing out one of the terms. So find the critical numbers of the function. So that means taking the derivative, in this case just setting it equal to 0. Find the open intervals on which the function is increasing or decreasing. So that's what we just did. We created the table. So you're going to have the same size table as I just used. I'll make it for you here on the page so you know that. Let me add a page. So you're going to need a table that is 5 by 4. So I'll fill in I'm not going to put the intervals in there. You can do that. So this is, the intervals go here. There should be 3 intervals. They go from negative infinity to something, and then this one goes to positive infinity. You'll have to put the other parts in. And this is where you pick the values of x that are in the interval. This is f prime at those values of x. Then you have the comments here, and you're going to draw a line to represent the comments over here. So in this one, you don't really factor. You're going to end up with x squared plus or minus something equals 0. Just solve for x squared. It'll be the result will be plus or minus something. And it's not an integer, so it's a radical. So yeah, so you take the square root of that.
Of negative 2?
It should be positive 2, because you're going to have this, when you move that to the other side, becomes positive. So this part, or this becomes negative, so they're both negative. So it should be x squared equals 2. Okay. Yeah. And then you take the square root of that, and you'll get plus or minus something. So what do you get? Plus or minus square root of 2? Yep. Okay. So it's really just the same as last time. Anytime you have a third order polynomial that just has x cubed, it always looks like this, and then it comes like that, and then it goes like that. So the only way, the other option is if it was negative, say everything was negative, so negative x cubed plus 6x minus 15. So just change the sign of everything. Then it's going to go like this. So you have your minimum first and your maximum second. But for a normal third order polynomial, you have your local maximum first, and then you have the local minimum. So, the other end, sometimes you have a third order polynomial and you don't have either a minimum or maximum. And that occurs when you take the derivative and there are no values of x where that goes to 0. So if I had 3x cubed or x cubed plus 6x, when I take the derivative, I'd have x squared plus 6x equals 0, and then you'd have a negative square root of a negative number, and it wouldn't work out. And you would see that there is no minimum or maximum. Let's just show that to you. So let's do this one. So this function is x cubed minus 6x plus 15. And we'll graph that, and we'll do that. And a lot of times you have to zoom out to be able to see it. So you can see this function has a local minimum at x equals negative the square root of 2 and a local minimum at positive the square root of 2. The function is increasing in the interval from negative infinity to the square root of 2. The function is decreasing in the interval between negative square root of 2 and positive square root of 2, and the function is increasing at x greater than the square root of 2. You'll notice that there's only one x-intercept. So there's only one real root of the original polynomial. And that's one of the powerful things about calculus, is that with pre-calculus, we'd been able to find this point, maybe not very easily. Doesn't look like it's a nice number. And we'd be able to find the y-intercept, which would be easy. And we'd have those 2 points, and that's it. So the question is, how do you draw the rest of the graph? Well, now that we have calculus, we can say, well, at negative the square root of 2, we have a local maximum. So we can actually calculate what that value is by plugging it back into the function. So I have that point up there, and I also can plot that point. And if you have the x-intercept, the y-intercept, and the minimum and maximum, that gives you a lot of information to be able to draw a pretty decent sketch that you wouldn't have been able to do if you didn't have calculus. We didn't do it in the problem, but it's easy to, what we would do is we would plug in the square root of 2, or negative the square root of 2 into this equation, and we would have gotten this value of y. And then we could do the same thing to get this value of y. So okay. So I'm going to go ahead and assign the homework for this section. What time is it here? Yeah. So what we'll do next time is I have a handout that, not next time as in Tuesday, but on Thursday. I'm thinking about it. I'll have to talk to Ian and what's his name? Sean. I may, on Friday, Friday we have the guest speaker coming in during physics. I may have physics, well, Evan, that messes up. I don't know if I was thinking of doing a physics lecture on Friday instead of a calculus lecture, because we're a little ahead in calculus. And so, what's that? You're fine with not having, so you wouldn't have to, you could sleep in, well, you have to take the bus, right? But you could, but anyway, so I may do that. I'll see if they should be available, because they're usually available for lab on Wednesday. So anyway, that was just me thinking out loud. So what we'll do, I have a handout for another example of this. I'll go through, you can see I have one more example, which involves a trig function. So again, we need to find roots and stuff like